So, we know now the limitation of CV. We can't the size, right, there is a limitation on size. If you have a particle smaller than, for an example, 30, 50, like 50 microns, it becomes really difficult to use sieving, right. So, we need a different technique. So, we will talk about laser diffraction, which is commonly used technique to determine the particle size distribution of powders, like any powder like cement or SCMs, right. So, what is the principle? We will talk about few salient features, like what is it about, then we will look at the limitations also, right. So, basically what is it? When incident light falls on a single particle, right, the light is scattered, okay, and this scattering is dependent on the size of particles. So, we are talking about the laser, right, it is a focused beam, and then scattering depends on the size of particle, the wavelength, polarization of the light and refractive index of both particle and medium surrounding it, and the particle has to be dispersed, right. You want to make sure there is no agglomeration, otherwise your particle size distribution will not be correct. So, usually your powders are dispersed, right, in medium. We will come back to it. So, a laser light passes through a dilute suspension or aerosol and is collected at low angles with respect to incident light. So, it is collected, that is why initially it used to be called as low angle laser light scattering. Okay. How do we then determine the particle size? So, we use we can use two theories, Fraunhofer's theory or Mie theory. Typically use these two theories for the analysis. So, Mie theory takes into account all the scattering phenomena by spheres of different sizes and requires knowledge of the complex refractive index. Okay. We will come back to it in the next slide, but Fraunhofer theory takes into account diffraction only, it does not require the refractive index. So, what is Fraunhofer theory? Fraunhofer theory assumes that particle being measured in is much larger than the wavelength of light. So, it is applicable to large size particles only, okay, first thing. The particles being measured are much larger than the wavelength of light, and all sizes of particles scatter with equal efficiency. These are some assumptions. The particles are opaque, transmitting no light, there is no transmission through particles. It predicts, how does it predict? It predicts the size based on a projected area. So, you have a particle, the projected area, okay, based on that it predicts the size. As is mentioned here, not suitable for small particles. So, if you have a smaller particles then of size less than 50 micron, then this theory is not suitable. So, for that we use Mie theory, it is applicable for whole range. So, it takes into account the optical properties. So, what happens when you have a small particles, there will always be refraction, absorption, right. So, it takes into account all these things, right, optical properties. So, what is the refractive index, what is the absorption index of your particle, right, of both materials and medium, right. So, it takes into account this absorption, refraction, which is not taken into account in Fraunhofer theory, and provides accurate results over a large size range. So, you see 0.02 to 2000 micron it can cover, and determines the volume of the particle. How does it work? It determines the volume of the particle. Okay. So, there are limitations with the Fraunhofer theory. So, most particle size analyzers use Mie theory, right, because it is first of all applicable to all, and also it takes into account the refraction and absorption which happens, especially in smaller particles. So, this is a schematic, you can see here you have a sample and you have a laser, right. So, you see this diffraction patterns, again the principle is same, you have a diffraction, when you have a constructive interference you have a diffraction. In this case we are talking about edged, so you have this particle, right. So, it is shown here, but see the difference when you have two different sizes, small versus big. Alpha 1 in the case of small is greater than alpha 2 in the case of big, right. So, there is a difference in the angle, diffraction angle, right, that can be used to get an idea about the size, right. Also intensity, now you see these rings, right, what you see, in the case of D1, where when your size is D1 is greater than D2. So, you have a difference in the intensity also, right, compared to here. So, there is a difference in the angle and also difference in the intensity. So, that can be used to determine the sizes.
So, those are the projected graphs?
Yeah, it is the diffraction rings, yeah.
So, where did they capture this?
So, yeah, so you have a sample and laser passes through the sample and you see these rings.
So, where do they
Detector.
Detector.
Yeah, yeah. So, but in real life you have a spheres of different sizes, right. Those are the idealized diffraction patterns that may not be exactly circular, right, because in real life you have a irregular sizes, right. So, for spheres of more than one size, the diffraction pattern is the superposition of the diffraction patterns from each of the particle size. Suppose you have a range. In real life you have assume that you have a spherical particles, okay, but the size changes, is different. So, they will all diffract differently, right, the angles will be different, intensity will be different. So, the net pattern which is this is the combination of the diffraction pattern for each size of particles, right. So, same minimization you have to do. So, what we do, how do we calculate then the number of particles, right. So, you see here this is the proportion of each size class, right, and you have a matrix where we are using something, because now we know that for one particular size you have a particular diffraction pattern like intensity, right, you are summing it up, right, and then minimizing the difference, you are assuming something, then minimizing the difference, because you have a diffraction pattern, then same thing measured versus calculated, right. So, these are the measured intensity for alpha 1, alpha 2, these are the sizes, right. So, that way we can calculate. So, idea again, see, you will get intensity like this, right, this is the net intensity, this is the combination of, see here you have a different patterns, right, this is the net effect. So, now you have to deconvolute it and tell what is the size, right, that is what it is doing. Okay. So, what are the assumptions and limitations, right? First assumption, we assume the spherical particle shape, okay. So, that tells you, like, if you have a regular size, you may not get the real picture, because the basic assumption here is the spherical particle shape. So, when particles are spherical, good correspondence with the image analysis. When the particles are spherical, then you have a direct good correspondence with image analysis, because in using image analysis you can see what is the size, you can verify it all the way down to 1 micron. For irregularly shaped particles such as cement, LD tends to broaden the distribution. Real distribution we are talking about, it will, compared to real distribution, it will tend to broaden the distribution. For anisotropic shapes such as rods and platelets, LD significantly overestimates the breadth and can give bimodal distribution for monodispersed cylinders. Yeah. So, these are some limitations you have to keep in mind. The refractive index. Mie theory requires the knowledge of complex refractive index of the material and fluid. We talked about, because it considers the refractive index, and complex refractive index can be written as, this is refractive index, K is absorption index, okay. For that you have to know, so this is the complex refractive, so for that you have to know N and K, that is the idea. So, Mie theory requires the knowledge of complex refractive index of the material and fluid. So, if you do not know, that will affect your results. Bimodal, when you plot distribution, you will see two peaks, the frequency, size, right. Normally what you do, if you have only, so this is normal. So that is just because of here anisotropic shapes. So what is the bottom line? Why we are talking about this? For non-spherical particle shapes, over interpretation of the PSD tails, like when we talk about 10% dV10 versus and dV19 90 should be avoided. We should not go too much into it, right, because we are talking about the tails. So dV550 is still okay, but too much interpretation of dV10 dV90 should be avoided, specifically if you have a non-spherical particle shapes. That is the bottom line. So how do you get a reliable particle size distribution? That is important, right. So because there are so many things which affect your particle size distribution. When we talk about the laser diffraction, see sample concentration. What is the sample concentration? Because you have to disperse in a solution. Normally we use isopropyl alcohol, like for cements, because we do not want to use water because it will react. But what is the concentration? If you have too small amount of cement, what will happen? Your signal to noise ratio will be very low. If you have too much, then you have a lot of scattering, that will affect your results. So it is important to pay attention to sample concentration. Dispersion, how are you dispersing? Because you do not want agglomeration in powder, because if you have agglomeration, that will again affect your particle size distribution. So usually we use ultrasonic treatment to de-agglomerate powder. Use stirring speed, powder flow rate, these are the things, stirring speed, right, how that can also influence your PSD. Measuring time, for how long you are keeping your sample, right, what is your measuring time, is it 1 second, 2 seconds, 10 seconds, 30 seconds for an example. Usually these laser diffraction is very quick, you get results in seconds. So which has, so you need to know what is the refractive index, and also you need to know what is the absorption coefficient, K, right, because that will affect your particle size distribution. Let us see here, how does the sonication affect your particle size distribution? So in this case, first of all, the sample is BFS slag, blast furnace slag, dispersed in IPA is isopropyl alcohol, okay, those are the conditions, and you are determining your particle size. In one case, in all cases they have 6 different samples, no ultrasonication, no sonication was done. Then you did 2 minute sonication, 4 minute ultrasonication, 6 minutes ultrasonication. See the effect. So clearly you see after doing sonication, your size, determined size has reduced, because obviously if you do not do sonication, there will be agglomeration. So the particle size you will get will be at higher end. Few minutes of ultrasonication can help you de-agglomerate the particles. But then beyond that you do not see much difference, so it is good enough. So 2 minutes of ultrasonication seems to work. This is for slag, so it will range from few less than micron to hundreds of microns.
So do we need to worry about the brittleness of single particle?
Maybe the large particles may have some issue in some cases, right, like if you are talking about 500 microns, right, when we are going higher end, might be issue, but that needs to be checked. Yeah.
Actually, it had a issue with this. After ultrasonification, there is a change.
Sure.
Glass, needed for the glass.
Okay. Yeah. So on higher, I can see. Yeah, it's possible. So that you have to be aware of.
So, but there is a rise at 4 minutes and there is a drop again to 6 minutes. What is the reason, sir? You can see that D50 also same. Why is that so?
Sorry, where did you say?
At the same level, below D50. There is a rise for 4 minutes sonic and the 6 minutes is coming back to what it was for 2 minutes.
Yeah, this one?
Yeah.
Oh no, sorry, this one. Yeah, there will be some differences, but I think
but again it is coming back.
yeah, I think what here the point is this in this case. The point is because if you have too much sonication also it may affect your yeah, but you need some sonication just to make sure that you de-agglomerate your powder, the particles. Okay.
For ultrasonic, the particles are agglomerated. After
Yeah,
you are
yeah,
doing it,
yeah.
size
So you see the reduction. Yeah.
okay.
So in this case you can see that 2 minutes ultrasonication is good enough. So yeah, obviously this limit will change. You know, frequency, all these things you will have to try on the material you work with, right? But the idea is we want to make sure that there is no agglomeration. You know, that's why we want to de-agglomerate the particles because that will affect your particle size distribution. Influence of optical parameters. Optical parameters. See, most diffracto laser particle sizes apparatus, they use Mie theory. Mie theory covers whole range of particles from less than micron to hundreds of microns, right? For that you have to assume the optical parameters. Assume means you have to know the optical parameters. That is very important. So here it shows simply how the values affect your value, you know, result. So again we are plotting particle size on y axis. N is the refractive index, right? And K is again, this is the imaginary part. We are talking about the complex. We are talking about complex index, refractive index, which is okay. So N is real part, K is imaginary part. Okay. So N is refractive index. Okay. Usually you have that information, and K is absorption coefficient. Understand? Because now we are taking into account both refraction and absorption, right? So it is important to know these N and K. Here it shows how it affects your values. So in this case when you keep N constant, N is 1.5. Now if you change K from 0, K 0 means no absorption, right? As you increase K, that means you are increasing the absorption, right? See the effect of that on the particle size. So you can clearly see there is an effect on particle size based on the value you choose. So here second one is for 1.56 N, and what happens when you go from 0 to 1, change K from 0 to 1. So the idea, the point is, it is important to pay attention to these model parameters like optical parameters. When you do particle size distribution like the experiment, you have to pay attention to this. You have to choose appropriate values, because if you choose N is normally easy to find because refractive index you can use the database, but if K, for an example, it is not that easy to find K. So for 0 you will have different value, like even smaller K, 0.001 will give you different value than, like this value is different than this, right. So that is why it is very important to pay attention to these optical parameters, because that affects your particle size distribution. So the significant variation in the particle size recorded using different optical parameters highlights the significance of detailed optical characterization prior to LD. So it is good to know these optical properties before you do laser diffraction. Suppose you are working with a material, you do not know any optical properties, then your results will not be accurate. You will get the results, but won't be very accurate. Okay. If you want to make sure, if you want to ensure the PhD results are representative, then knowing these properties help. As you see here, because these will affect your particle size distribution. Okay. Finally, this is master sizer 3000 by Melbourne Analytical, a typical apparatus instrument which we use for particle size analysis, right. And this is the typical output. What do you get? The output is you have a distribution. This is from the software, the software you get the distribution. Okay. I will end here. Basically what we do, we plot the cumulative percentage with against the size. So, on x axis you have particle size, on y axis you have a cumulative percentage, right. So, basically that means if you have a this, right. So, for this percentage, maybe it is 0.25, 25% particles are below 40, okay. Yeah, so only difference between left and right is in the left here you have a normal, like normal axis, here you have a logarithmic axis. You see what happens, your size changes drastically, right. We are not talking about 10, 20, 30, 40 microns, we are talking about 0.1 to hundreds, 200 microns. So, usually x axis you have logarithmic. So, here is the logarithmic. When you plot your cumulative, it looks very same, only thing is like you have changed your x axis from normal to logarithmic, right. That is the only difference. Okay, we will stop here.